Program Management Leader and your host for today's Vulcan Flight Readiness firing. I'm here at the Advanced Spaceflight Operations Center at Cape Canaveral Space Force Station in Florida. Twin BE-4 engines is scheduled within the window this evening. The team is currently coordinating a new T0. Testing can often be challenging, so the team planned a window of time to work through any necessary issues. This is a test of the booster engines, so the booster will be tanked and pressurized. We also will tank the Centaur for this test, as it provides the needed ballast or weight, but Centaur will be kept at standby pressures. In addition to watching our live coverage, you can also follow progress at ulalaunch.com and on social media. The count is currently in a planned hold. We have 2 planned holds in today's launch count, which give our team additional time to resolve any issues prior to entering the terminal count. In a few minutes, launch conductor Dylan Rice will poll the team for the final go to pick up the count. As you can see, we are currently in a storm here at Cape Canaveral, so we are working through weather coordination with the Eastern Range and coordinating a new T0. We'll resume some of our commentary once we have more information, and we'll take a look at some of our live pad shots in the meantime. This is Vulcan mission control at T-minus 7 minutes and holding. As you can see, weather is improving as our team works to establish a new T0. While we wait, let's learn more about how the Vulcan rocket is.
Following the journey to Cape Canaveral, the Vulcan components are offloaded from rocket ship and transported to the VIF, where they are lifted onto the newly constructed Vulcan launch platform, or VLP. The vehicle then travels a third of a mile to the pad to fill both propellant tanks, followed by flight readiness firing of the booster stage.
This is Vulcan mission control at T-minus 7 minutes and holding. Let's hear from Vulcan Certification Flight 1 Mission Manager Lauren Sanders about our upcoming first launch. This is Vulcan Mission Control at T-minus 7 minutes and holding. Manufacturing a new launch vehicle is no small feat. The Vulcan Centaur rocket would not have been possible without the team in ULA's Decatur factory. Let's hear from ULA leaders about this exceptional group of rocket builders. This is Vulcan Mission Control at T-minus 7 minutes and holding. Today's flight readiness firing tests the Vulcan rocket with its new BE-4 engines. Let's learn more from ULA's BE-4 Certified Responsible Engineer, Kurt Ingram.
Hi there, I'm Kurt Ingram. I'm the Certified Responsible Engineer for the BE-4 engines. I'm in our Decatur, Alabama factory, and I'm standing here in front of our first Vulcan rocket with our first two flight engines. When we perform our flight readiness firing with this rocket, we'll do the full countdown, tank the rocket, and then ignite the engines. The plan is to throttle up, hold that power, and then do a normal shutdown, and then all the, of course, post-shutdown detanking and safing activities involved with that as well. These engines use a lot of new manufacturing techniques, which is something that is important in these new rocket engines to improve manufacturability. It brings down the cost of the engine and increases the production rate. The BE-4 engines use liquid oxygen and liquid natural gas. One nice thing about that is after you've tested the engine, it's very easy to clean up the engine and restart it again. It also has improved properties in the combustion devices, the cooling passages of the thrust chamber. And overall, it's a propellant that we believe has a lot of promise and has a lot of benefits for the Vulcan rocket. These two particular engines went through a rigorous test program in Texas. They each had at least 2 acceptance firings to prove that they're ready for flight, and they successfully passed all those tests and were delivered to us and are now ready for launch.
This is Vulcan mission control at T-minus 7 minutes and holding. Vulcan's first stage is powered by methane propellant. The use of this fuel has several advantages. As a highly efficient propellant, it delivers a high ISP, meaning more miles per gallon. It's non-corrosive and non-toxic, allowing for safer use at the launch pad compared to hypergolic propellants. It requires storage at a more manageable temperature and requires less storage capacity compared to hydrogen. It possesses clean combustion characteristics even at low throttle, simplifying engine reuse compared to kerosene fuels. Using an oxygen-rich staged combustion cycle, a single BE4 engine is capable of producing 550,000 pounds of thrust. The engines at the base of the Vulcan rocket are made by Blue Origin. Let's learn more from their team.
The BE4 rocket engine is a 550,000 pounds of thrust, liquid oxygen, liquid natural gas, oxygen-rich staged combustion engine cycle.
One of the most important things about building a road to space is making sure it's affordable, and a key piece of that is going to be making sure the engine is also affordable and cost-effective.
It's difficult because the rocket engine produces a tremendous amount of energy, which puts the hardware under physical stress.
It's a high-pressure environment, high-temperature environment. You've got moving parts.
You have to design durability into the system. So pushing the material, pushing the system performance, pushing all the components.
The propellant combination that we run on is liquid natural gas and liquid oxygen.
Liquefied natural gas is one of the most cost-effective rocket fuels around.
The LNG is also a clean burning fuel, which is really important.
It's an incredible piece of engineering that we built here in Kent and that we test in West Texas and soon our Marshall Space Flight Test Center at 4670. You can hear the rumble and feel the energy of the BE4 engine.
Raw power.
We put the engine through its paces. We try to break it on the test end so we know exactly what the limit of the design and build processes have become.
It's a pretty exciting time on BE4 at this point. We've completed all of our pre-qualification testing. We've moved into engine production.
BE4 is going to be the workhorse of the 2020s and the 2030s.
To be able to support an engine through the development and production and seeing them integrated onto Vulcan and flying is going to be something that I will never forget.
This is Vulcan mission control at T-minus 7 minutes and holding. The launch site underwent significant modifications to make Slick 41 a dual-use pad to seamlessly handle both the Atlas V and the Vulcan manifests simultaneously. Some of the work shown here included a new methane storage area featuring 3 reservoirs, upgrades to the booster liquid oxygen transfer lines, larger cryogenic storage tanks for Center 5's liquid hydrogen and liquid oxygen, and updated acoustic sound water system, and changes to the vertical integration facility to accommodate the larger diameter of Vulcan. The Cape also has a new dedicated Vulcan launch platform and refurbished a Titan-era facility known as the Spaceflight Operations Center, or SPOC, to house the rocket. The graphic shown here details Vulcan's journey to the launch pad. This new next-generation rocket provides a higher performance and greater affordability while continuing to deliver our unmatched reliability and precision. Once production is complete, the rocket transfers to our rocket ship and is transported to the launch site. Then our launch processing begins with our launch vehicle on-stand operation. After that, we'll proceed into our flight readiness firing, the milestone we're working towards here today. Once our testing has completed, we'll proceed into standard processing operations with our payload mate, and then countdown, fueling, and launch of the first Vulcan. This is Vulcan Mission Control at T-minus 7 minutes and holding. Vulcan is a game changer for our customers. Gary Wentz, ULA's Vice President of Government and Commercial Programs, shares what it means for the future.
This has really been a team effort working across the country. Our Decatur team with production operations, our West Coast team getting ready and doing the preparations to be able to support future launches, and folks in Florida with launch operations, as well as our customer community that are likewise spread across the United States. Since we started the development of the Vulcan launch vehicle, we've been working hand in hand with our government customers to make sure that as we go forward in the design, it meets all the requirements. The Vulcan launch vehicle offers us a single configuration core vehicle to be able to fly all the spacecraft. Everything from our commercial satellite providers to our national security space customers and eventually our human spaceflight customers. I've worked in the industry for over 30 years, and you don't get the opportunity to launch a first flight of a vehicle that often. This is very exciting to be here and be ready to fire the engine on the launch pad for the first time.
This is Vulcan Mission Control at T-minus 7 minutes and holding. As expected, when preparing for a new rocket, modifications have to be made to the launch pads. Renovations have been completed at Slick 41 here on the East Coast, but let's learn more about modifications planned for Space Launch Complex 3 on ULA's West Coast launch pad.
Hi, my name is Paul Aragon. I'm the West Coast Launch Operations Director out here for Vandenberg Space Force Base. Behind me, you can see there's an Atlas vehicle sitting in our mobile service tower right now. As we bring the Vulcan vehicle in, we will certainly have to make modifications to the platforms and the doors, obviously to make room for the larger diameter of that vehicle. Also on the umbilical tower that's off to the right of the MST, that'll also get modified. We have umbilicals that'll be swinging over, making their necessary connections to both the booster and the upper stage of the Centaur and the payload fairing. Inclusive with this particular set of mods out here, we do have a fixed launch platform, which is different than our East Coast mobile launch platform. Ours will include a mast, just like the East Coast, all of which fully supports tanking, providing commands to the vehicle, and obviously eventually launching our vehicle. This is the locked storage area for the Atlas rocket. This will be the home to the Vulcan locked storage area as well. Off right down in front of me to the left is the booster storage tanks for Atlas. Those will become the storage tanks for the Centaur 5. We're going to have to add some capacity for the Vulcan. We're going to take away quite a bit of the earth here, bring it down, and put a very large 250,000 gallon tank that'll include vaporizers and offload station, and that'll be home to our new Vulcan storage area. This is the side of the pad that has our fuels and our gas storage area. We do have water for deluge to the pad, but off to the left here and working backwards to the very far back is our gas storage area, and that'll have both our gaseous helium and gaseous nitrogen. We will be bringing in more of each of those because obviously the Vulcan rocket demands more. The yellow tanks you see back here, that's strictly for Atlas, RP1. Those tanks will be drained of their propellant, and then we will go ahead and remove those from the complex, and we'll bring in some of those vessels that we're going to use for gaseous nitrogen and helium. If I go and I step back here on this side, this will be where we're going to have Centaur hydrogen, and Centaur is going to be bigger as well, so we're going to have to increase capacity. We're actually buying a brand new 70,000 gallon tank to complement our existing tank, and that'll make up the total volume that we need to fuel the Centaur vehicle. 2 offload stations will be here, which is only 1 right now. And so that again will help us to be able to not only be ready for a first attempt, but be ready for multiple attempts. Right behind me, it's going to be home to our new liquid natural gas facility. It'll have a 250,000 gallon brand new tank. It'll have a knockout drum, an LN2 tank that'll do conditioning for the propellant. And then it has an offload station to include burn-off flares to take any of that gas that's either coming from the vehicle or the storage area and burn it off so that we can control anything that's going into our atmosphere. Well, thank you. I hope you enjoyed the overview here for the complex and look forward to modifications for Vulcan Centaur coming to the West Coast.
This is Vulcan Mission Control at T-minus 7 minutes and holding. Last year, ULA's Atlas V rocket launched the Low Earth Orbital Flight Test of an Inflatable Decelerator, or LOFTED, proving the capability for reuse on ULA vehicles. Let's hear more about this successful test.
Customers. We know it's all about lowest dollars per spacecraft for these large constellations. And so reuse is an important lever for us to continue to provide and drive down that lowest dollar per spacecraft, not only for our US government customers, but also for our commercial customers, specifically Amazon and the Kuiper program.
This is Vulcan Mission Control at T-minus 7 minutes and holding. The Vulcan rocket we're seeing today has a distinctive look. Here's a behind-the-scenes view at how this was accomplished. You may also notice that the Vulcan logo is covered in a layer of ice on both the booster liquid oxygen and liquid methane tanks. These aluminum tanks are uninsulated, so condensation freezes when the tanks are filled with cryogenic propellants. The portions of the vehicle without ice are composite structures, or they're covered in SOFI, spray-on foam insulation. This is Vulcan Mission Control at T-minus 7 minutes and holding. Building rockets requires a large team, more than just the ULA team. At ULA, we have a team of over 45 suppliers that span 22 states. 20 suppliers in addition to our Colorado and Virginia sites as well. This is Vulcan Mission Control at T-minus 7 minutes and holding. The Vulcan Centaur rocket was developed with a low-risk path to first flight. 90% of the capabilities and designs of the Vulcan rocket will be flown before the actual first flight. The program was developed by leveraging our heritage vehicles, Atlas and Delta, and using some of those technologies to give us this heritage experience and flight heritage as we lead to the initial ILC. So as you can see, some of the items like the payload fairing, the pressure stabilized stainless steel tanks, and structurally stable aluminum tanks go all the way back to our heritage vehicles. In addition, we've on-ramped some capabilities over several cut-ins of the Atlas and Delta vehicles to get us some flight heritage here over the last several years. Some of those capabilities included updating our payload fairing manufacturing process and modifications, now flying dual RL-10 engines, updates to our common avionics system and software, and then most recently implementing new SRBs that have flown first on the Atlas vehicle. So ultimately, here at our first flight, we have several flights across all of these components, and the BE-4 engines are truly the first flight component on the Vulcan vehicle. This is Vulcan Mission Control at T-minus 7 minutes and holding. ULA's Atlas rockets have launched many of the world's vital space assets. Let's take a look at the impressive legacy of the Atlas family of rockets, which has significantly contributed to the development of Vulcan Centaur.
And the RD-180 engine roars to life and liftoff of the maiden flight of the Atlas V rocket with a Hotbird 6 spacecraft on board.
As the inaugural flight of the Atlas V lifted off on August 21, 2002, it carried with it the dreams and aspirations of thousands of rocket pioneers who had laid the foundation that made it possible. Atlas V continues the Atlas legacy of innovation and accomplishment that has been vital to our nation for more than half a century. Named after the mighty giant of Greek mythology who carried the world on his shoulders, Atlas was conceived as a weapon and a deterrent, but evolved into a system that pushed the envelope with trailblazing innovation and steadfast reliability. At the request of the Air Force, Charlie Bossert and his San Diego-based engineering team began work on a
advance.
3 provided a substantial performance improvement over the Atlas IIAS. Reliability was increased by reducing the number of engines from 8 to 2 and the elimination of 5 staging events, as well as more than 10,000 parts.
This is Atlas Mission Control at T-minus.
In 1998, the Atlas team embarked on a development project for the United States Air Force that would forever change the Atlas vehicle.
And the RD-180 engine roars to life and liftoff with a maiden flight of the Lockheed Martin Atlas V rocket with a Hotbird 6 spacecraft on board for Eutelsat in Paris, France.
From
This is Vulcan Mission Control at T-minus 7 minutes and holding. ULA's Delta IV Heavy is the nation's proven heavy lifter. Let's take a look at the evolution of this impressive rocket.
exploration missions.
+4, 3.
This is Vulcan Mission Control at T-minus 7 minutes and holding. ULA also launches Atlas and Delta rockets here in Cape Canaveral, Florida. Let's take a look around.
With missions launched to every planet in the solar system, as well as critical national security, science, weather, and communication satellites, ULA has established a long-standing reputation for reliability and orbit accuracy in the space launch industry. At our launch site in Cape Canaveral, Florida, the story begins with ULA's Atlas and Delta rockets arriving on the RS rocket ship. The rocket ship is a specially designed cargo ship used to transport rockets from ULA's 1.6 million square foot production facility in Decatur, Alabama. Rocket ship is large enough to carry a complete Delta IV Heavy rocket. That's 3 boosters, a second stage, and a payload fairing. Once loaded, rocket ship departs ULA's dock and travels through the Tennessee River, then onto the Ohio and Mississippi rivers, then goes out into the Gulf of Mexico. From there, the ship travels through the Atlantic Ocean, around the southern tip of Florida, and north to Port Canaveral. Rocket ship was designed with several features to ensure successful delivery. including the ability to adjust its draft for shallow water and rudderless steering, which minimizes the need to tug. Atlas V boosters are transported from the ship to the high bay in the Atlas Spaceflight Operations Center, or ASOC, for final preparations. Delta IV boosters are moved to the Horizontal Integration Facility, or HIF, where they are mated together to form the Delta IV Heavy configuration. With final checks completed, the boosters are transported to the launch pad for Launch Vehicle on Stand, or LVOS. The 107-foot-long Atlas V boosters are brought to Space Launch Complex 41 and are hoisted into a vertical position using a crane and placed onto the Mobile Launch Platform, or MLP, in the Vertical Integration Facility, or VIF. Delta IV Heavy rockets are raised vertically by a fixed pad erector at Space Launch Complex 37. The fixed pad erector uses a single hydraulic piston to rotate the boosters 90 degrees inside the Mobile Service Tower, or MST. LVOS is followed by the addition of solid rocket boosters, and then the second stage. Next comes Wet Dress Rehearsal, or WDR, which is an end-to-end launch simulation, from fueling through spacecraft separation. Meanwhile, the ULA team is also working simultaneously to help the customer encapsulate their payload into the rocket's payload fairing. The encapsulated payload fairing is the final piece to be mated to the rocket. With the rocket stack complete, the spacecraft team tests all of the interfaces with the rocket and the launch pad. Once the rockets are completely assembled, final launch preps begin. For Atlas V rockets, launch countdown begins with moving the rocket from the VIF to the pad. The quarter-mile trip uses 6 components to complete the 20-minute trip. Weighing in at about 2 million pounds, the MLP supports the rocket and contains air conditioning, electrical, and commodities, while the undercarriages bear the weight of the MLP and rocket. 2 rail cars lead the move, with the payload van providing communication to the payload, while the ground van houses the ground support for the rocket. At the rear of the convoy, the portable environmental control system provides air conditioning to the payload and rocket. Finally, track mobiles provide the power to move the 3.5 million pound convoy. For Delta IV Heavy rockets, the process looks quite different. Approximately 9 hours before T0, final preparations begin as 40 hydraulic cylinders at pressures nearing 3,500 psi move the 10 million pound MST. It's first raised 8 inches and then rolled back. Delta uses a carriage transporter system, traveling at about a quarter mile per hour. It takes about 25 minutes to roll the MST to its launch position, 345 feet north of the Delta IV rocket. The Delta IV rocket stands 217 feet tall, or about 21 stories, and weighs more than 900,000 pounds fully fueled. On the day of launch, nearly 30 engineers and managers are polled for system status and readiness to proceed.
Status check to proceed with terminal count, Atlas Systems, propulsion.
This is the final status check before launch for all Atlas and Delta vehicle systems, ground systems, the spacecraft, and the U.S. Air Force Eastern Range. The vehicle system readiness poll includes electrical systems, hydraulics, pneumatics, propulsion systems, flight control, and propellants.
Range coordinator. Clear to proceed. Launch director.
Launch vehicle is ready to launch.
Mission director.
This is the mission director. You have permission to launch.
Proceeding with the count.
If the rocket is ready for flight and the weather is within the launch commit criteria, then polling will be completed and the team will have given the go for launch.
T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. There's ignition. And liftoff of the United Launch Alliance Atlas V rocket.
For a typical Atlas V flight, the main engine and solid rocket boosters ignite to lift the rocket off the pad. Shortly after liftoff, the rocket begins a pitch over to attain the proper flight path, minimizing the dynamic pressure the vehicle experiences during flight. Within the first few minutes of flight, the vehicle reaches Mach 1, the speed of sound, followed by jettison of the solid rocket boosters. About 4 minutes later, propellant levels deplete and the booster engine shuts down, followed by release of the booster stage. At various times in flight, depending on the mission, the vehicle jettisons its payload fairing. From there, the second stage will continue carrying the spacecraft towards its destination with planned engine starts and stops. Finally, Centaur will release the spacecraft in its target orbit to continue its journey.
This is Vulcan Mission Control at T-minus 7 minutes and holding. We just received confirmation from launch conductor Dylan Rice. Our new T0 is 9:05 p.m. Eastern Time. ULA builds Atlas, Delta, and Vulcan rockets in a 1.6 million square foot facility in Decatur, Alabama. Here's a look inside.
Successfully launching missions
As we talked earlier, we've made modifications to Slick 41 so that it can support both the Atlas and Vulcan launch systems, making it the only operational dual-use pad. As you can see here, this is the new launch platform that is specific to the Vulcan vehicle. Also at the pad, we've added additional fuel tanks, enabling the ability to supply liquid methane to the booster stage. We've also updated the acoustic water suppression system to protect the pad during engine firing. Vulcan was designed to be similar in height to the Atlas vehicle to enable many of the key interfaces between the vehicle and launch infrastructure to remain unchanged. This is Vulcan Mission Control at T-minus 7 minutes in holding. In a few minutes, launch conductor Dylan Rice will poll the team for the final go to pick up the count. While we wait, let's learn about today's flight readiness firing from ULA's President and CEO, Tori Bruno.
This is such an exciting day and one that we have worked so hard to reach. The first Vulcan flight rocket is on the launch pad. Flight readiness firing, or FRF as we like to call it, is a full vehicle tanking and engine hot fire for several seconds. The FRF includes tanking of the Vulcan booster and Centaur 5 tanks to assess pre-launch procedures, including a terminal count demonstration starting at T-minus 7 minutes and culminating in a short duration engine firing. Test takes place at Space Launch Complex 41 at Cape Canaveral, the only currently operational launch pad capable of launching 2 different rockets. Objectives for the PTT and FRF include systemic validation and testing of flight-configured launch vehicle and its associated ground support equipment, including demonstration of day of launch integrated closed-loop control of vehicle systems and the VE4 engines. Confirmation of operational readiness of vehicle airborne and GSE systems, facilities, as well as ground and flight software. So truly an end-to-end preparation and practice for that big launch. Demonstration of successful vehicle commanded engine start sequence and shutdown is also part of this, as well as validation of operational timelines and sequences. The test approach for PTT number 2/FRF allows us to buy down risk as we demonstrate the system in a measured manner. Such an exciting day. Go Vulcan, go Centaur, go FRF.
We remain in the planned hold as we continue towards FRF. 29 engineers and managers are polled for system status and readiness to proceed. This is the final status check for all Vulcan vehicle systems, ground systems, and the U.S. Space Force Eastern Range. The vehicle system readiness poll includes electrical systems, hydraulics, pneumatics, propulsion systems, flight control, and propellants. Let's listen in as Dylan Rice performs the final polling.
All steps complete prior to the status check. LC switch is ready. Status check to proceed with terminal count, Vulcan systems, propulsion. Go. Hydraulics. Go. Pneumatics.
Go.
Go. LNG. LO2. LO2.
Go.
Water.
Go.
Centaur systems, propulsion. Go. Pneumatics. Go. LO2.
Go.
LH2.
Go.
Has gas.
Go.
Electrical systems, airborne.
Go.
Ground. Go. Facility.
Go.
RFFDS.
Go.
Flight control.
Go.
GCQ.
Go.
Operations support.
Go.
COM.
Go.
Umbilicals.
Go.
ECS.
Go.
Red line monitor.
Go.
Quality.
Go.
Op safety manager.
Go.
ULA safety officer.
Go.
Vehicle system engineer.
Go.
Anomaly chief.
Go.
Range coordinator.
Clear to proceed.
Launch director.
Launch vehicle is ready for FRF.
Mission director.
You have permission to execute FRF.
Proceeding with the count. ALC, verify T0 is set for 01, 05 Zulu. Verified.
Polling is complete. The ULA team is go for today's flight readiness firing. A few minutes before firing, you'll be listening to Dylan Rice and his team performing the final steps in the countdown procedure. Several critical activities occur in the final minutes, including verifying fuel tank and pressure levels in both the Vulcan booster and the Centaur upper stage. Within the final 15 seconds, you'll hear Go FRF. This is the final status check of the Vulcan and Centaur readiness. At T-minus 7 seconds, the ROFIs, or radial outward firing igniters, ignite. At T-minus 5 seconds, start command is sent to the engines. At T-minus 3 seconds, the main engines ignite to demonstrate BE-4 operation in the integrated vehicle system. At T0, the BE-4 engines will throttle down, mimicking the nominal shutdown that typically occurs at booster engine shutdown, or BECO. Before we continue, let's check in on the weather this evening. Ground winds are 5 knots out of the south, and the temperature is 77 degrees Fahrenheit. There are no concerns for rules. This is Vulcan Mission Control at T-minus 7 minutes and holding. We anticipate releasing the hold in just a few moments.
3, 2, 1, mark. 655. Ground pyros enabled.
The countdown clock has resumed, and we are go for flight readiness firing at 9:05 p.m. Eastern. A few minutes from T0, we'll raise the volume on our team so you can hear the final preps taking place. This is the first time the team will fire up the Vulcan rocket's BE-4 engines at Space Launch Complex 41. Let's learn more about this innovative rocket. This is Vulcan Mission Control at T-minus 3 minutes 54 seconds. For today's test, we have support from our Launch Console operators and engineering teams at both the ASOC here at the Cape and in Colorado at our Denver Operations Support Center. While today's test is primarily about testing the vehicle and ground systems, it also serves as an opportunity to train and certify our launch team to support the first flight of the new Vulcan vehicle. This vehicle configuration is unique to the FRF test, with no spacecraft, payload fairing, or SRBs. After a successful FRF, the vehicle will be inspected and reconfigured into the flight article. It will then follow our standard processing operations, and the encapsulated spacecraft and SRBs will be mated before launch.
Two minutes, 38 seconds. 2 minutes, 30 seconds.
You may also notice that the Vulcan logo is covered in a layer of ice on both the booster, LOX, and methane tanks. These aluminum tanks are uninsulated, so condensation freezes when the tanks are filled with cryogenic propellants. The portions of the vehicle without ice are composite structures or are covered in SOFI, spray-on foam insulation.
Vehicle internal. Hot sequencer start.
1 minute, 50 seconds. One minute, 40 seconds.
Launch enabled.
1 minute, 35 seconds.
FTS armed.
T-minus 90 seconds. The rocket, ground systems, and eastern range are go.
1 minute, 20 seconds.
SCS count started.
Sixty seconds.
We're about 1 minute away.
Vulcan tank set step 3.
Ground vent valve secured. Go, FRF.
T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2. We have ignition.
LC switch not ready.
Like ready to reset clock to T-minus 7.
LC, reset clock, countdown clock to
We
T-minus 7.
just saw
minutes and holding.
ULA's Vulcan engines throttle up for the first time.
LC, this is Peony 1.
Go, Peony 1.
Vulcan tank pressures are stable.
Rice announced ignition, power, and shutdown of Vulcan's twin BE-4 engines. The team is now looking at how the engine operated, analyzing data from the firing, and safing the vehicle as we prepare to detank.
Go ahead.
I'm looking for a status at step 40.
X in chill mode.
Roger.
And LC, this flight control.
Go.
Step 60 SBAPS. SS.
Once we start detanking and the booster tanks start to warm up, the Vulcan logo will reveal itself again. The rocket you see at Slick 41 today is the same vehicle that will be launching the first certification flight. Let's learn more about how it's built.
Following the journey to Cape Canaveral, the Vulcan components are offloaded from rocket ship and transported to the VIF, where they are lifted onto the newly constructed Vulcan launch platform, or VLP. The vehicle then travels a third of a mile to the pad to fill both propellant tanks, followed by flight readiness firing of the booster stage.
This is a huge accomplishment. In just a moment, I'll have the opportunity to speak with ULA's Vice President of Vulcan Development, Mark Peller. Before he joins us, let's take another look at the exciting final moments of the count through firing of Vulcan Centaur.
16.
Ground vent valves secured. Go, FRF.
T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, we have ignition.
LC switch not ready. Countdown clock to
We
T-minus
just
7
saw
minutes and holding.
ULA's Vulcan engines throttle up for the first time. Hi, Mark. Thank you so much for joining us. We've just watched the flight readiness firing of the Vulcan vehicle. Congratulations. How are you feeling?
Thank you, Amanda. Well, a whole range of emotions, obviously. Super excited, relieved, I'll be honest, and just very gratifying. A lot of hard work by the whole team, many, many years of work to get us to where we are here today.
Absolutely. And this was a really big milestone on our path to first flight. Can you talk a little bit more about what this test was and what the objectives for today included?
Sure. This is a huge milestone. This is as close as you can come to launching a rocket without actually launching the rocket. So complete integrated test of all the airborne elements, the ground systems, all coming together, putting it through everything that we would on a normal day of launch, obviously up to including actually starting the main engines, everything short of releasing the rocket. So significant development, really signifying significant progress. Our last major milestone on the path to launch. So big accomplishment.
Yeah, and you mentioned the development. Designing, building, testing a new rocket comes with a whole bunch of challenges. Can you talk a little more about the Vulcan team and what it took to get to this point?
Sure. Well, when we talk about the Vulcan team, it's really the whole ULA team contributed to this. We may have started out many years ago with a small team, but this is our future. This is a ULA product, and everyone at ULA has played a significant role of this, and this is the future, and this is what we'll all work on down the road. A significant accomplishment that when we started out, we had a group of folks that had extensive experience, building and launching rockets and designing missions and integrating payloads. And one of the keys to the success of Vulcan was taking all that experience and really using that to develop a next generation rocket. And that's what we've done with Vulcan, and it's going to serve us very well.
Can you talk about what this test really meant to you personally? I know you and the whole ULA team have worked really, really hard to get here.
Well, yeah, like we said, it's one of the last significant milestones on the path to launch, so it's tremendously gratifying. It's one of those things, until you actually see it, it's hard to actually envision. You're sitting there, you've looked at that hardware in some cases for years, stationary, and while it wasn't lifting off, to see it actually functioning with the engines firing and all the systems working together is just, as I said, it's terribly exciting, very gratifying.
Absolutely. Well, again, congratulations on getting to this monumental day, and thank you so much for joining us.
Thank you.
This is Vulcan Mission Control. I'd like to congratulate the entire ULA team on getting us to this historic day. Stay updated on Vulcan next steps by following our live blog at ulalaunch.com. I'm Amanda Sterling, and thank you for joining us. Before we sign off, we'll take another look at our successful flight readiness firing, which occurred at 9:05 p.m. Eastern Time. 8, 7, 6, 5, 4, 3, 2. We have ignition.
LC switch not ready. Countdown clock to
We
T-minus
just
7
saw
minutes and holding.
ULA's Vulcan engines throttle up for the first time.